So, welcome to massive open online course on fluidization engineering. This lecture will be on elutriation characteristics in the fluidized bed. We have discussed the entrainment characteristics in the bubbling as well as first fluidization condition. So, this elutriation characteristics also is the same way to discuss how to actually the particle is separating along the axis of the bed. Here also that mechanism is the same way that the fine particles will be just segregating from the fluidized bed along the axis, and the entrainment mechanism also will be some extent it will be useful to analyze this. So, what is that actually elutriation? Elutriation that defined as the classifying effect of the fluidized bed entrainment. It characterizes the selective removal of the particles of individual size from the fluidized bed. So, this is the definition, and this elutriation rate is generally being denoted by notation Ws. Which is exactly the unit for that solid flux here. W is unit is that means kg per meter square second, and this elutriation rates from the vessel which freeboard height is greater than the TDH, that will be should be remembered. Now, what is that importance that for which you have to know that elutriation characteristics in the fluidized bed. Now, you know that entrainment rate that has to be known for the design of gas solid separators like cyclones or filters. In the same way, elutriation is also important because this gives you the classification of the solid particles, which particles will be go up, which particles will go down, what should be the interaction of the larger particles or coarser particles with the smaller particles, and because of that interactions how the solid particles would be segregating by the entrainment mechanism there. On the other hand, you can say the less amount of solid particles will be coming down relative to the finer particles if there is high interaction inside the bed, and there will be a formation of the fine particles because of the interaction, and in that case the very fine particles will be coming out easily relative to the coarser one. But if coarser one particles, the strength of the particles actually in main factor, if the strength of the particles is not that much enough, so that the coarser particles sometimes by their individual interactions may be forming finer particles, and then it will go up. So, based on which that you can say how the solid particles also will be segregating from these two classes of the particles there. So, the loss of bed material that is related to the entrainment may be important for the technical and also the economic success of a fluidized bed applications there. Sometimes you have to operate the fluidized bed in such a way that there is no enough elutriation or there is no attrition of the solid particles, because of which that entrainment characteristics will go down. So, sometimes these fine particles the internal circulation of the fine particles is required for the better transport operation, and in that way sometimes the economic operation of the fluidized bed can be done in such way by designing with those considering those entrainment and elutriation characteristics of the particles inside the bed. And it characterizes the selective removal of particles of the individual size from the fluidized bed. If you are going to segregate the particles from this bed, then there will be a certain selection or selective removal of the particles of the individual size from the fluidized bed by this elutriation mechanism. Determination of the elutriation rates, you have to know how to actually estimate the elutriation rate. Two different approaches actually you will get to find the elutriation rate. One is called that is Jens et al. Approach, another is elutriation constant approach. Now, both the approaches actually based on the assumption that the flux rate of any particular size of solids I is proportional to its weight fraction x in the bed, and all other factors kept constant. So, this is very important that you have to know the elutriation rate. Generally in the literature it is given two types, one is Jens et al. Model, another is elutriation constant model. They are, in that case for both the cases you have to actually assume that the flux rate of any particular size of the solid that should be proportional to the weight fraction of that particular classes solid in the bed. All other factors, if you are keeping constant and G s I is equal to x I G s I star, in that case G s I star is the flux rate from an imaginary bed of solids all of size I, thus it is saturated carrying capacity of the gas, or that you can say that the exit concentration, dilute exit concentration at a fixed rate there, and for that the particular size of solids will be coming out from the bed. So, in this case the rate of the elutriation you have to calculate by this denoting by G s I for this particular class of particles, that will be equal to x I into G s I star. So, I means here class of particles, at a particular class of particles here I. So, G s I means here the solid entrainment of that particular class. That means, if the particle size is suppose d p I, that means that class of, then it will be represented at that finer or coarser of that particular classes, that will be equal to what should be the weight fraction of that particular classes I particles, and also what should be the carrying capacity or saturated carrying capacity of that particular gas for those solid particles of class I. So, from this equation you will be able to calculate the elutriation rate. Now, Jens et al. Model, as per that Jens et al. Model, you will get the different step to calculate that elutriation rate here. Now, as a step 1 you can say that this distribution of the particle that will actually roll enough there. So, you have to divide the size distribution of the particle into narrow intervals, and then you have to find the intervals in such a way that for elutriable solids, that means U f is less than U, that means here, or U t here, so this U t elutriable solid. In that case the terminal velocity should be is less than fluid velocity, then only those solids will be elutriable. And for non-elutriable solids, the terminal velocity of the solids will be greater than fluid velocity. Of course, the coarser particles, those who are terminal velocity is higher than the fluid velocity, those particles will not be entrained at all. So, it cannot be actually elutriable or cannot be segregated from the fine particles there. And if it is less than suppose terminal velocity, then only it will be elutriable, and then those particles will be segregated from the coarser particles whose terminal velocity is higher than the fluid velocity there. And in the step 2, find then G s I star for each interval of the elutriable solids. So, first you have to find out which one is the elutriable, just from the terminal velocity of the solids and what is the fluid velocity, whether it is greater or less than, then you can find out which one will be the elutriable. Once you know the elutriable solids, and then find the what is the G s I star for each individual of elutriable solids from the curve shown here in this case. And this is this curve, actually this figure is representing the this saturated carrying capacity versus this what is that some parameters here. So, then from which you will be able to calculate what will be the this figure you can get it from that Cooney and Levenspiel also, there it is given. So, once you know this G s I star from this figure, and then you have to calculate the G s here from this equation like this here. So, for each class of particles you have to get the respective G s star. So, once you know that, you have to sum up all these parameter here in this case. So, G s to be calculated by this equation 2. Here again for this continuous size distribution, you can calculate this elutriation rate by this equation 3 here. So, here G s will be equal to integration for all particles, it will be G s I star into P e into d p into function of P e as a function of particle diameter into d d p. So, in this case you will be able to calculate what should be the that means elutriation rate. This here P e d p is nothing but the particle size distribution function. The elutriation constant approach here, it is called sometimes Labha 1951 and Yagi and Cooney approach also. So, now with particles of wide size distribution in a bed with a freeboard whose transport disengagement height is actually less than this freeboard, the flux of particles of size I out of the bed can be expressed as by equation 4 here. See here, this is the 1 minus 1 by 80, it is the cross sectional area of the bed, and here dW, this is what will be the amount, that means mass of solids of size I which is changing with respect to time, that the rate of that mass of this elutriation, that will be equal to k I star into x I or is equal to k I star into W I by W here. This x I is the mass fraction. So, this is W I of the W weight of the or mass of the ith size particles, and W is the total mass of the bed here all for all classes, where k star is called the elutriation rate constant. This k I star, it will be is equal to G s star as per equation 1 which refers to the flux rate of solids I if they are alone in the bed, and k I star will be equal to 0 which refers to the flux for those solids that are not removed at all by entrainment, and k star that will be very large which refers to the rapid removal of that size of the solids from the bed. Now, is there any other alternative way or not? That there is one alternate way of elutriation rate that can be calculated. Now, if we represent this rate of removal of the solid of class I which is proportional to the weight of that size I of the solids in the bed, then what should be that proportionality constant, that will be the k. So, this k is different from here k star. So, if we represent this elutriation rate by this simple equation, and this rate which is directly proportional to the weight of that size, not weight fraction there. So, in that case this proportionality constant will not be the same as whatever in the previous equation it is represented. So, or you can say that minus d W I by d t will be equal to k I W I, k I the unit will be second inverse here. So, comparing this 4 and 5 equation number, then k I star that will be equal to k I W by A T, A T means cross sectional area of the bed, and then it will be equal to k I rho I into 1 minus epsilon m f m into L m. So, from this what should be the relation between k I star and k I, you can get it. So, k I is simple, that it is that elutriation is directly proportional to the weight of the solids, whereas k I star it will be represented by that the rate equation will be actually proportional to the mole fraction, or you can say the weight fraction of the solids of class I there. Now, significance of this k I and k I star, that is the elutriation rate constant. Now, k I star is equal to G I star as per equation 1, which refers to the flux rate of solids if they are alone in the bed, and k I star is equal to 0, which refers to the flux for those solids that are not actually removed at all by the entrainment. And this elutriation rate will be very large if the rapid removal of that size of the solids from the bed is happened, and k I varies inversely with the bed height. In bass or unsteady state experiments, it is seen that k I should change during a run as the bed weight W is changed. On the contrary, you can say that K I star is unaffected by these changes. It is the true rate constant and is the quantity to use when reporting data and presenting correlations there. And relationship between K and G S. Now, for a elutriable single size eye of solids, you can say the carry over from the vessel is represented as this K I star, that will be equal to G A star or is equal to saturation carrying capacity of gas for solids I. If the fluidized bed that consists of coarse solids plus only one size of elutriable solids of mass fraction x I, then the total carryover will be equal to x I into K I star. So, that will be equal to x I into that means G S I star. Now, here if the bed contains coarse solids plus sizes like 1, 2, 3 dot n, that means n different size of solids which are elutriable, and then the total entrainment will be equal to G S, that will be equal to their summation of I is equal to I to n x I into K I star. That means, here for all solid classified particles, there you have to sum up all those things. Now, summation of x I should be less than 1 there, and if all the bed solids are elutriable, then only you can say that summation of this mass fraction of all classified will be equal to 1. Now, alternatively, if one considers a continuous size distribution in the bed, then the total flux of elutriated solids will be calculated as this G S will be equal to here K star into P B d P into d of d P here. Now, these expressions for fluxes are applicable only for the bed height that is greater than the transport disengagement height. So, it is to be noted down. Now, how to estimate K and K star experimentally? Now, solids flow experiments here you will see that one is steady state operation and steady state recirculating system, and there will be a steady state once through system, and another important experiment the batch experiment. You can estimate this elutriation rate by these two types of experiment there. So, solid flow experiment, as per solid flow experiment you will see that you have to measure the carryover rate and the weight fraction of the size in the bed, and then from equation 4 or in terms of a continuous size distribution, if it is given to you of the bed solids, then you have to determine K star as here this K I star, that will be equal to flux of I from the bed in kg per meter square second upon weight fraction of ith solid particles in the bed, and that mathematically you can say that G S into that means P into d P, that means here solid particle size distribution, and divided by P B into d P here this again this weight fraction of the bed, that means represented by this distribution. Now, as per batch experiment, in this experiment you have to first find out the initial bed composition and the composition with respect to time. Now, if the total mass of bed does not change significantly, that means less than it is 20% in a time, then integration of the equation 4 will give you that W I by W I 0, that will be equal to exponent of that means here minus K I star into a bed into T by W and that means here exponent of minus k I t. So, from this equation 12 you can get what should be the actually elutriation amount of solids of class I from this equation. Now, if the bed weight changes significantly during the experimental run, that is if most of the bed solids are elutriable, then measure all the size fractions before and after the run, and naming the elutriating size fractions 1 to n and the non-elutriating fraction of I. After that you have to integrate the equation 4 and then rearrangement you can calculate W 1 by W I 0, that will be equal to W 2 by W 2 0 and to the power k 1 star by k star is equal to this as per equation 13, and from which you can calculate that k I star that will be equal to this as per equation 14 you can calculate this k I star. Now, measuring the bed composition before and after a run and inserting into equation 13 that will give you the ratio of k star values. Then equation 14 gives k I star here, and from which all other k star values can be found here. Now, some important correlations for k I star as per different investigators from their experimental results. It is given in Kuhn-Levenspiel textbook, then you can get. So, these are the different correlations from which you can get this k I star. So, these correlations will be helpful to know this k I star for designing any fluidized bed, and all these things they have all this k star given by different investigators. They have correlated this with the experimental condition, like here terminal velocity of the fluid, particle diameter, and velocity of the fluid, particle size, density of the gas, and density of the solid, and minimum fluidization velocity, and also the terminal velocity for that particular classes of solids, and also what will be the significant group. As per that is given this terminal Reynolds number based on terminal velocity, and Froude number based on that particle diameter, and also relative velocity of the fluid relative to that terminal velocity of the particle. And also based on different type of solids, they have also got the different correlations. You can get more information from the Kuhn-Levenspiel book for more correlations also. So, these correlations very important to calculate how to calculate the k I star, and from which what should be the elutriable amount of solids in the fluidized bed for that particular operating condition you will be able to calculate. Some other correlations also given here. See, in this table there are different correlations also given for predicting the k I star in the fluidized bed from their different experiment and within a certain range of their particular experimental condition. As per different investigators, they have suggested different correlations, and they also obtained that experimental results of this k star based on their by using different operating condition and solid particles there. So, these are some other correlations by which you can calculate the k I star, elutriation rate constant. Now, let us see one example to calculate this elutriation rate there. Now, a fluidized bed of 6 meter diameter is operating with catalyst particle under the following operating conditions. Here the gas density is given, here density of the solids and the fluid velocity is given, particle size is given, and the freeboard height is considered is greater than transport disengagement height. So, in this case you have to calculate what should be the saturation carrying capacity, calculate the saturation carrying capacity for a bed in which the fines constitute just 20% of the bed solid, calculate the total entrainment and the solid loading at the exit port of a bed of fine catalyst here. And it is given that this particle size distribution is that for different particle size here in the table, this function is obtained from this table for this PDP here. Now, just calculate the u this group u 0 square by GDP rho s square, and once you know this value. So, from this figure you just calculate what should be the group G A star by rho z u g for that particular value of this u square by GDP rho s square here, and from which you will be able to calculate what would be the G A star, that means saturated carrying capacity. And then from equation 1, then G A star will be equal to this once, and from equation 3, then G S by rho s u 0 will be calculated as per this here after substitution of this what is that size distribution and integrating with the size range of 10 to 130 micrometer here. And what should be the density of the rho s? Here it is bulk density of the solids, here it is given here solid loading you can calculate from which then after that total entrainment amount you can calculate from this equation. Now, what should be the elutriation rate constant K star for 40 to 120 micrometer particles from a experiment at 1040 kilopascal, and the fluid velocity is 0.381 meter per second. Now, in this case what is the Gs? That it is very simple to calculate from this figure A. What will the Gs you can calculate with respect to this velocity of fluid here. And after that find the size distribution function for bed particles here PDP and entrained particles PEDP from figure B here. And finally, then K star values for the various particle size are found from equation number 11 and are tabulated as follows here. So, in this way you can calculate the elutriation rate. Another example, calculate this K star values from various correlations in the literature for the fine elutriable fractions present in a bed of coarse and fine particles there. So, in this case again you can calculate here this correlation value in this case, and then different correlations you just use these correlations you can use from this table, and based on which just you can get that with Yagi and Ashish correlations, this you can get this K I star as this, and here Wen and Hashinger's correlations you can get K star is equal to 2.16, whereas with Merrick and Higby correlations it will be 0.834, and other correlations will give you the different value like this here. So, as a summary you can get that if you increase the particle diameter, you will see Yagi and Asi it will decrease the constant for this elutriation, and for Wen and Hasinger it is seen that also here it will increase and then decrease, and Merrick and Higby as per that it will decrease and decrease very it is substantially decreasing that with respect to particle size. Geldert et al. It is seen that also the particle size will decrease the elutriation rate. Jens and Weil it is seen that as per this particle size again this elutriation rate will decrease, but Gugnoni and Jens et al. As per their calculation for their correlation it is seen that also this dP will decrease the that is rate constant there. So, very interesting that we can then calculate what will be the elutriation rate from this lecture, and what is the elutriation rate, what are the different methods to calculate or estimate the elutriation rate, and what is the elutriation rate constant, and based on the different experimental condition how this elutriation rate can be estimated by different correlations that we can get from this. So, this will be helpful for the design of further information and further understanding of the fluidization phenomena inside the bed. Okay. So, our next class onward will be our next lecture will be something else on that fluidized bed we will be discussing later on. Thank you.